So we've talked about the link between integrals and area. So here I want us to estimate the integral between 0 and 2 of this function. And I don't want us to actually find the equation and take the antiderivative. I want us to do it by thinking about areas, because we know that the integral means the area underneath the curve. So if I make I've got a diagram here, and between 0 and 2, I'm talking about this area right here. And I don't really need a fancy calculus lesson to figure out what that area is. That area is the area of a triangle, which has the formula 1/2 base times height. And the base is this distance right here, which is 2, and the height is 3. So the area for this is 3, or the integral would equal 3 units squared, if you want to put units to it. So now let's keep going and say, what would be the integral between 2 and 4 of this function? And if I interpret my integral as the area between the curve and the x-axis, then what I'm saying is find the area between the yellow area right here. And that is approximately looking like a semicircle. So it's an estimate here, that's what that's about. So I'm making my best guess and saying, yeah, that looks like a semicircle. I've got a formula for the area of a semicircle. It's pi r squared divided by 2. And the radius in this case is 1. So it's pi over 2. All right, now let's go one step further and say, what is the integral between 0 and 5 on here, 5 of this function? So what we need to do is calculate all the areas and do the arithmetic. So we said this one was 3. Let's put that one in, put them in black. This one was 3. This one was pi over 2, and I should have made that negative. Why? Because it's below the x-axis, so that's negative pi over 2. So I made a pretty big mistake there. So that's negative pi over 2. And then let's do the last area in gray. So that's, oops, gray. So that is an area of a triangle, which is 1/2 base times height. So 1/2, the base is 1, and the height, let me just estimate that. I know I don't have great, I'm just going to call that 5, 2. So that the height is 2. So that means the area here is 1. So that area is 1, and it's positive 1 because it's above the x-axis. So, sorry, this is not the area. Here, this was wrong. This is not the area between 0 and 5. I was just doing, the one I calculated here is just between 4 and 5. So let me fix that. So that was between 4 and 5. So putting it all together, if I wanted to figure it out between 0 and 5 of this function, I could just consider all the areas and add them together. So that would be 3 for the first piece, minus pi over 2 plus 1. So the total integral would be 2 minus pi over 2. And yes, you could find the formula for each of these and integrate, but sometimes looking at the area is a way more efficient way to do it. So let's do that now with a couple more questions. This time I'm not going to give you the graph. I'm going to say estimate the area given that function, and you can do it using integration techniques or antiderivative techniques, but I'm going to do it using the area first. So this is an equation of a straight line and a y-intercept of 1 and a slope of 1, so something like this. And at 0 it's 1, and at 3 it would be at 4, so it's 3, 4. It's that point right there. So my question, this really means find the area between the curve and the x-axis. So that says that I am finding the area, let me do that in a different color, this area right here. And that is the area of two things. It's the area of a rectangle and the area of a triangle. So I'm going to do, or you could do it as a trapezoid if you remember that formula, but I'm going to do it as the area of this rectangle and the area of this triangle. So area 1 is length times width, and area 2 is a triangle 1/2 base times height. So the length of the rectangle is 3, the width is 1, and of the triangle, it's the base is 3, and the height, this height of the triangle is also 3. So that means the integral is equal to 3 plus 9 over 2. And if I simplify that using common denominators, I get 15 over 2. So the integral is 15 over 2. We could check this by doing it algebraically as well, so maybe I should do that at the same time. So I'm going to do this again. This time I'm going to use my knowledge of antiderivatives. So I'm going to take the antiderivative, which is x squared over 2 plus x, and right now it's a definite integral, so I don't have to worry about the constant, and I'm going to evaluate it at 0 and evaluate it at 3 and subtract the 2. So I'm going to evaluate it at 3 first, which is 9 over 2 plus 3. There it is at 3, minus evaluated at 0. So 0 over 2 plus 0. So my integral again is this, which will be 15 over 2. So it agrees with my area interpretation of the integral. So one last one is I want to do this one again using a diagram and thinking of it as areas. So I've got an absolute value function that's moved to the right 2. So it looks like this. And I want to find the integral between 0 and 2. So that means between 0 and 2, so that's the area in between the x-axis and the curve. And so that's just a simple triangle, so it's 1/2, the base is 2, and the height is 2. So the area under the curve is 2, which means this integral is 2.